All right, good morning. So as you said, my name is Andrew O'Brien. I'm a research scientist at the Electroscience Lab at OSU. I'll be talking about GNSS-R, and since I'm following Chris's presentation, Tianlin asked me to sort of not talk about the basic stuff, but a little more extended applications, and so I'll be talking about two different topics regarding that. All right, so just setting the stage, what is our motivation here? And that's over the last 5 years, there's been this surge in activity using GPS and GNSS signals reflected off the Earth's surface for remote sensing. We call that GNSS-R. And the GNSS receiver and the GNSS satellites form this unique passive bistatic L-band radar system. And it's already been mentioned before, but because it's a receive-only instrument, you can make them less expensive than traditional radars, form large constellations, and enable new Earth observing strategies with these constellations. And we use the amplitude, the phase, the polarization, and other properties of these reflected signals to retrieve geophysical properties. And so in this presentation, I wanted to talk about two different topics. The first one Chris had just alluded to at the end of his, which is coherent GNSS-R measurements. So this is one of the sort of more exciting and promising features in GNSS-R today. So I'll be talking about the difference between coherent and diffuse, and I'll be showing how we use the Cygnus raw sample data to take a closer look at these coherent scattered signals. And then for the second half of my presentation, I'll talk about polarimetric GNSS-R measurements, which is something Cygnus can't do. And we have to use a different satellite, the SMAP satellite, to actually receive reflected GPS signals and look at their polarimetric properties. And so I'll talk about that too, to sort of expose you to both these topics. Okay, so Chris already introduced Cygnus. Of course, this constellation of 8 microsatellites receiving GPS L1CA coded signals. It was designed to measure ocean surface wind speed. However, recently, Cygnus has many interesting land applications, right, that people have been investigating. And so to introduce you here, this is the actual Cygnus level 1 data. Again, the video is a little choppy. But these are the 4 GPS reflections measured by one Cygnus satellite as it flies over the Amazon region. And whereas all the DDMs Chris was showing was this nice horseshoe shape, which is the diffuse scattering we expect over the ocean. Over land, things are much more complex, right? We have inhomogeneous scenes with land, and we have inland water. They're coherent or non-coherent scattering, and all these complex spatial mappings of the reflections into delayed Doppler space. But as you can see, there's a lot of these very sharp signals, right? And these are our coherent reflections that are going to be occurring as we see reflections of inland water. So very similar to what Chris had introduced, right? So the idea between coherent and diffuse scattering is that when the surface is very smooth, we get a mirror-like reflection and different scattering equation. Whereas over rough surfaces like dry land or the ocean surface, we have sort of random rough scattering over a large area like the glistening zone. And this is completely analogous to what we observe in the reflected GPS signals. So for a smooth surface, we'd see a strong mirror-like reflection of the direct path GPS signal. And then over a rough surface, of course, we're over a larger area, this rough surface scattering and occupying a large portion of delayed Doppler space. Okay, and so it's the fact that these coherent signals are very much stronger than the diffuse scattering that we can make interesting maps like this. So this one is generated by accumulating just the basic SNR measurements that Cygnus makes over 1 month onto a map. And because, as Chris mentioned, the coherent reflected signals are 20 to 30 dB greater on average than the signals reflected off land and the ocean, we can clearly pick out the different water features, wetlands, and rivers and lakes and so on. Right, so this is what compelled a lot of research today. And as Chris had mentioned, if we compare the types of quality maps that Cygnus can make to traditional water masks generated using optical techniques, it really does highlight the ability of Cygnus to penetrate vegetation and be able to detect water features hidden beneath canopies and so on. And so, that motivates us to look more into coherent scattering. So, what makes coherent scattering different than the other types of scattering? And that's, we have both amplitude and phase information technically available to us. And the spatial region over which that measurement occurs is not this large glistening zone, but is the first Fresnel zone, which is typically less than 1 kilometer for Cygnus geometries. And so this opens up a lot of interesting applications, wetland monitoring, flooding and inundation, river flow rate, as Chris mentioned. As we get towards grazing angles over the ocean, we can do centimeter level ocean altimetry. Sea ice, particularly fresh sea ice, it responds very coherently. So we can do sea ice altimetry detection and even thickness measurements, and then separate water from the soil moisture measurements and so on. So there's lots of applications for dealing with coherent reflections rather than diffuse. Unfortunately, the Cygnus data product has really been optimized for the non-coherent ocean measurements, right? So we're integrating for 1 second non-coherently and sort of destroying the additional information that's underneath this. However, there's a special data collection mode in Cygnus that we take advantage of that allows us to study the coherent reflections in more detail, and that's the Cygnus raw AF mode. And so the Cygnus satellites can be commanded to collect short 60-second bursts of raw signal data. And so this is the signal samples essentially right after the A to D. And the sampling rate is about 16 megahertz, although the front-end bandwidth is 2.4 megahertz, so this is the real bandwidth of the signals we're receiving. It's recorded for all 3 antennas on each Cygnus satellite, and the files are provided with a bunch of metadata and made available to the Cygnus science team. This slide just shows a snippet of the available files to give you an idea. Basically, these are commanded based on request, and so there's a variety of different science team members requesting files over the Amazon River Basin, over the Mediterranean and Indonesia, over different lakes in China, wetlands, and so on and so forth. So there's quite a nice amount of data that you can process yourself, these raw signals. And so we've been doing a lot of research into doing that. And so here's just one example to give you a feel for what one of these raw tracks looks like. Here's a case over a lake in China, right? And we have this GPS reflection track over crossing the lake. We can see the DDM has that strong coherent shape. Down here we have the SNR. So we're seeing over the course of this track, over land we had SNRs in 2 or 3 dB, but then over the lake we're in the 15 to 20 dB SNR range. And so this just really gives you a feeling for what these coherent reflections look like, and this is done using the raw sample data that Cygnus occasionally collects. And so what we do is we use this data to look for cases where we detect coherent scattering. All right, because with the Cygnus raw AF data, we can change the way the DDMs are generated. We can adjust the coherent integration time to make it longer, to increase the SNR of these coherent reflections. We can decrease the non-coherent integration time to improve our spatial resolution, so we're no longer smearing so much along track. And we can adjust these things in different scenarios and investigate what we're seeing in different scenes. And this allows us to develop a simple coherence detector based on this idea that looking at the change in the power we observe by changing the coherent integration time, does the power change like a coherent signal would, or does it change like a non-coherent signal would? And so we can detect at the sort of most basic level, is there a coherent reflection present? And then we've been doing that to look at a number of different raw AF collections over land and see what we observe, see when we observe coherent scattering. And so here's the first case. This is in Tennessee. So this is a 60-second raw AF track of 1 GPS satellite. And we have the color-coded here. So red is whenever there's non-coherent scattering, and green is whenever coherent scattering is present. And so you can see the sort of percentage of time the coherence detector is above a certain threshold. And really, this is just a random track, say, through Tennessee, but we're getting about 20% of the track being coherent. So there's quite a bit of coherent data out there, right? But if we zoom in on any one of these green portions of this curve, we pretty much always find that there's a water body present, all right? So like here we're looking at one example where we have the track, right? This is the 100 millisecond of DDM that's been produced with the raw AF data. And we see it's green because the coherence is present. And here's the water body that's underneath that track. Now, this one is a separate case where there's a track and the water body is actually slightly offset by a few hundred meters from the actual track. But again, coherence is detected. And if you were to go through, we find basically that whenever there's coherence, there's always water. And whenever there's non-coherence, there's always no water, all right? So it's a lot of evidence that we're only observing coherence over inland water. Here's another case. This one is over Kentucky. Again, gives you a sort of feeling. This is just a random track through the US, right? You can see the sort of percentage coherence we're observing. And not only that, but there's a lot of cases where we're detecting coherence where the SNR is actually very weak, right? So it's not necessary that, when we go over a water body, that we'd always get a very strong SNR, because that water body might be very, very small, or it might be a little bit farther away from our track. But our detector is still able to detect that there's coherent present, despite that low SNR, which gives us the idea that we can start really detecting very small water features. And so here's an example of some of the smallest features we've detected. So here's a sort of arbitrary looking farmland. Here's our GPS track, and there's some coherence that's been detected within our track, right? Which isn't very obvious at first. And then if you search around these farm fields, you'll eventually find these tiny ponds in various places. And so here are two example ponds we've detected. So this one is about 100 meters across, so it's quite large. This one is only 47 meters. And so, these ponds are easily detectable in this Cygnus data, and we even get carrier phase measurements from these portions. So we could actually use that phase information to, say, do altimetry for these water bodies. Here's an even more extreme case where, again, we have some coherence detected, right? And this is actually a sort of 5-meter wide creek going through this area here. Again, showing that, as Chris mentioned, the water body could be a very, very small portion of the actual Fresnel zone area, which is this black curve. So this is the first Fresnel zone as it's traced along the long track direction. And then that would be the small portion of that that's actually corresponding to water. So here's a sort of alternative case where there is no coherence, right? This is over the southwest US. And, as I mentioned, when there's ever dry land, when there's forests and no water bodies present, we never seem to detect any coherence. And this is actually supported by theory, of course. Coherent reflections at GNSS frequencies really can only occur over portions of the surface where the roughness and height variations are only a few centimeters, right? So we can, very intuitively understand that there's very few land features that would ever be that smooth, to have a sort of few centimeters of RMS height. And so, we never detect coherence over land, essentially. Similarly, for here's a case in the desert in Libya. Again, no sort of coherence detected here. So, alternatively, in wetland areas, that are seasonally flooded, like this area in Bolivia, when we make this map, we see this gigantic red area, and this is the seasonal flooded floodplain here. And we get incredibly strong coherence, right? So, that makes GNSS-R in general a very hot topic for wetland monitoring and inundation detection. And here's another case over the Amazon where, we get coherent detections over obviously visible water, like these rivers, but there's coherence that also occurs over areas that are basically, if you zoom in, it's just a forest canopy. Again, sort of showing that we can detect water hidden beneath there. And the final example, coherence is never detected pretty much over the open ocean. However, there's lots of coastal areas that have strong coherence, and whenever there's a sheltered harbor, like we see here in the Bahamas, we get strong coherence over these portions of the water, though. So, well, this gives you sort of an idea. Basically, when we're talking about water surface roughness, due to wind or waves, how much can we tolerate, how much before it becomes transitions from coherence to non-coherence. And for that, we can use a simple exponential model based on the RMS surface height. And so this curve is showing essentially the attenuation for different RMS surface heights for different incidence angles. And in general, we see basically if we're going to be about 10 dB or 20 dB down, we're in the range of 2 to 4 centimeters of RMS height before that water surface would become too rough to detect coherently. Let's see. All right. And so I think this has been mentioned before. The spatial resolution of these coherent reflections are based on the Fresnel zones. So if we show essentially the phase of the reflected field over a surface, we'd see these concentric rings of phase. And in this particular geometry I'm showing, which is a 50-degree incidence angle, we can see the size of the Fresnel zone is approximately 1 kilometer one direction, approximately 800 meters in another. And so this is sort of the basic spatial resolution we expect out of these coherent reflections, although the actual details are more complicated. I'm going to skip through a few of these for the sake of time. All right, so that was the first half of this presentation, just talking about how we use Cygnus raw AF data to look at these coherent reflections. In future instruments, we'll be able to utilize the phase information from these coherent reflections in a better way and hopefully enable more applications, things like centimeter level height measurements and additional science. And so that's sort of our active area of research. So that brings us to the second part that I wanted to discuss, which is polarimetric GNSS-R measurements. So this is something quite different, right? So we're not using Cygnus for this study. We're using actually the SMAP satellite, right? So SMAP has a L-band radar and radiometer. The radar transmitter amplifier failed back in July of 2015. And so the receiver has been tuned to the GPS L2 band, which allows the radar receiver to at least receive GPS reflected signals off the Earth. All right, and that's interesting to us because SMAP is equipped with this incredibly high gain 36 dB dual polarized rotating reflector antenna. And so it provides this very unique opportunity to look at both reflections in dual pole and with a high gain. So the SMAP antenna is different than Cygnus. The Cygnus antenna is sort of fairly wide beam that allows GPS reflections in very easily, while the SMAP antenna has this narrow beam that rotates, right? So instead of always getting a nice picture of a GPS reflection, we have to sort of coincidentally rotate the antenna beam through it, right? So it's not a continuous measurement, and it's quite tedious to find situations where that beam happens to hit reflections, but it does. The SMAP data is unique in that it collects the INQ samples at 1.25 megahertz sampling rate and actually downlinks these samples to the ground. So we're able to do whatever processing we want on the ground. And so we developed custom software to form delayed Doppler maps of GPS reflections from these signals. And this is what a SMAP DDM looks like. Okay, it's quite a bit different than the traditional Cygnus DDM, right? We still have the horseshoe shape. However, we're seeing farther out in delay because we have this higher gain antenna. We also see this sort of ghost duplicate waveform, right? And this is actually due to some of the radar data blanking and the filter responses of the switching inside the SMAP radar receiver. And so that causes that ghost, but we're still able to use this sort of DDM data in the same way one would with Cygnus. This I had mentioned before, where due to the small antenna footprint and the rotating antenna, we're actually quite restricted in the amount of data we're able to get out of SMAP. So the top plot is showing 1 day of the SMAP orbit in terms of all the GPS reflections that should be visible from it. However, if we incorporate the actual antenna pattern as it's rotating, we only keep sort of small glimpses of these reflections, and this ends up being the sort of daily sampling period of this data. And so it results in a sort of revisit rate of several months, right? So it's not good, that's not that great for doing science, but it is good for doing research studies. As I mentioned, SMAP is unique when compared to Cygnus, right? So we have this dual polarized antenna rather than a LHCP antenna. Instead of 14 dB gain, we have a 36 dB gain. We have a polar orbit instead of this 35 or 38 degree inclination. So Cygnus is limited to the tropics, where we get the entire Earth with SMAP. And as I mentioned, we get raw data, so we are able to process these samples any way we like, whereas with Cygnus, we get sort of fixed DDMs coming down to the ground. So this SMAP, one of the key things that's going to be good for investigating is polarimetric measurements. One key component of making good polarimetric measurements is to have good antenna cross-pole isolation. And this is actually quite difficult to achieve. If you've seen studies, people doing polarimetric measurements with GNSS-R from airborne and other cases where, to to do this type of work, you need to have a very good cross-pole isolation, so you can isolate the different components of your polarization. And with SMAP, this is sort of taken care of for us because it's such a well-designed antenna. I'm showing here the copole and cross-pole components of this antenna gain. And if you were to do the ratio of these two, the cross-pole isolation in the center of the main beam is on the order of 40 to 50 dB. So it's an incredibly good system for looking at these effects. So here are some polarimetric DDMs generated using SMAP. So this is a GPS reflection over the ocean. As I said, SMAP has H and V channels. We can calibrate those and combine them to produce LACP and RACP. So in this case, over the ocean, we see H and V components, but if we convert those into left and right, we see that over the ocean, we pretty much only see a left-hand scattered reflection and no right-hand reflection, despite the antenna gain should allow us to see this even if it were a weak signal, but in fact we don't see any. So this is as theory predicts and what we observe.
Do you know how windy this was?
I don't think I have it recorded somewhere now. So this shows the same idea, only in animation form. Okay, so we have the SMAP satellite moving, and this red dot represents the location of a GPS specular reflection point. We have the SMAP antenna pattern represented by this green circle as it is rotating, and we can see as that antenna pattern gets closer to the specular point, it reaches the peak of the horseshoe pattern in our DDM. And this is over the ocean. As you can see, there's no right-hand component visible, which is similar to other sort of compact polarimetric instruments. But what we do is we can form primarily the ratio between the left-hand and the right-hand components, and the ratio of those amplitudes has information in it. We can also do other things like form the complex correlation coefficients between DDMs of different polarizations, and then we get a sort of complex, correlation magnitude as well as phase. So, what are applications of GNSS-R polarimetry? So, one of the more obvious ones is soil moisture. All right. So, Chris had shown some soil moisture measurements from Cygnus, and those are developed using different retrieval techniques. But you have these factors of surface roughness and vegetation that need to get mitigated. And one way to do that is to use a polarimetric measurement. So if you take the ratio of the left and right powers, these effects more or less cancel, and you have sort of a sort of soil moisture sensitivity in this ratio of polarimetric amplitudes. The plot shown here is a simple model sort of demonstrating the polarimetric ratio and its dependence on soil moisture as a function of different incidence angles. So, we use the SMAP data. We have to measure the polarimetric ratio. So I'm showing the ratios here for 2 different months, 2 different seasons. And we're using a model that I showed in the previous slide to predict what that polarimetric ratio should be based on sort of SMAP measured soil moisture, and then showing the actual SMAP GNSS-R measured polarization ratio and how this corresponds very closely to what we predict based on the model. And so this is showing that our GNSS polarimetric measurements are sensitive to soil moisture in the way that we expect. Here's a second case, again showing 2 different seasons for a different area over Mexico. We're showing the predicted polarization ratio based on models and what we measure. And again, these 2 curves and the trends are very similar. So just demonstrating what we can do with that. All right, so using SMAP for GNSS-R is a very interesting research topic just because the high gain and the dual pole provides this very unique tool. The raw signal data lets us design new processing techniques and particularly into polarimetric measurements. SMAP is very limited in terms of its antenna footprint. So these data sets aren't good for large-scale science, but they are good for research, especially when we're trying to make decisions about future GNSS-R instruments and how they should handle polarimetric measurements. Okay.
Any questions? You mentioned for the repurposed use of the radar component on SMAP. You're assuming that the transmit signals are all perfectly RHCP, right?
Mm.
From the different satellites, though, I have to imagine there's probably some variation there, or are they all truly perfectly and consistently right-hand circular polarized?
I guess I don't know offhand any measurements that have been done to sort of verify the polarization
And
purity. Yeah.
Are they stable and similar too, right? Or, you know, if you have a satellite 1 compared to 13, that there's actually, you could have a difference there which could cause other issues down the train.
Yeah, I mean, that's an interesting point. Yeah, I've never been able to find any sort of data to help, yeah.
But we know they're not identical.
Well, yes, they're not identical. In terms of what their cross-pole levels actually are and are there differences, I'd imagine there are, but I don't know the exact level, yeah.
Thank you.
Yeah, especially, you know, following that same question, you know, if you go up the bore side of an antenna, the degree of CP will change.
Yeah, that's true. So I think, I mean, from the GPS satellites are much higher altitude, right? They're MEO, and the actual angular range that we're in from the transmitter perspective is somewhere on the order of 10 degrees. Yeah, it's a question.
All right, thanks a lot.